Good afternoon, everyone. Just before we start, and to avoid confusion after, normally you should have a little piece of paper like this on your table, or sometimes on your chair. If you don't, I have a few extras here, and I say a few, that's like 3 of them. So if you opted for ground seating and need one of those, I have them here. And another thing before we start, be kind to the Wi-Fi, please, because you're going to use it. We're not going to use it extensively. It's going to be like gentle and everything. But if some of us are streaming videos or whatnot, it's going to make it a rather unpleasant experience for everyone. So please be kind on the Wi-Fi. Resist the temptation to use your hotspot because it will just make everything worse for everybody. That's it. All right. And without further ado, so I'm Jérôme Petazzoni. I'm currently presenting from a Linux machine that doesn't have proper Unicode support, and so you can see the collection of emojis that I'm desperately trying to adopt as my middle name, because since I immigrated to the United States, I noticed everybody had a middle name. So normally that's whale emoji, ship emoji, and package emoji, which means that Docker ships containers. And I have the ghost avatar of AJ Bowen helping me. I will explain shortly exactly how she's going to help during this workshop, but she's delivered many workshops like that with me before. This is going to run from 3:30 to 5 p.m. It's going to be rather fast-paced, not because this is usually a full-day workshop and we're going to compress it in 1.5 hours. No, that's not the reason. Just because there is still a lot of content that I want to cover. Don't panic. I'm not going to show you the whole one-day thing because that would be completely insane. All the content that you will see today is available online in a GitHub repo. The slides, the code samples, the scripts that I use to create the environment, everything is available. And so you're welcome to borrow, steal, reuse, adapt as much as you like, the things that you like. Feel free to interrupt with questions at any time. You can either do that with the classic old raising your hand, or you can also use the chat. I happen to use Gitter for that, and I will give a few details in a minute. As I said, there is a full-day version of this, and the support is available online if you want to revisit this content later. So brief introduction, this was initially written for workshops like this, but then we realized that this doesn't scale very much because there are some ethical problems and liability with cloning people. It doesn't work as well as we thought, and so instead of cloning me, we decided, okay, let's have a self-paced version that people can just follow along by themselves. We try to have as much information as possible on the slides, but sometimes you will be stuck, and in that case, you can refer to the awesome Docker documentation or the forums or Stack Overflow if there is really no other solution. So this is the content that we will cover today. So first, I'm going to talk about the pre-requirements and the VM environments that we're going to use. Then we are going to run a little microservices application on a single node. Then we will see that it doesn't scale. It never scales anyway. So we're going to see how to scale that out using SwampKit. We will build our own Swarm cluster. We will see exactly what's behind the marketing motto, build, ship, and run any app anywhere. We will see that there is actually like this build, ship, and run thing corresponds to very specific steps. We will set up a self-hosted container registry. We will deploy the app on our cluster, and we will see how to do rolling upgrades. And if we have some time, I will add a few words about the least privilege model because it's a really cool thing in SwampKit. Okay, so pre-requirements. For this workshop, you need to have a computer, check, an internet connection. I have a wired connection because I cheat. You only have the Wi-Fi, which is why you should be kind with the Wi-Fi. And all you need on your computer is not even Docker or anything like that. You just need a web browser and an SSH client. Why? Because if we have VMs or containers and whatnot on our local machines, at the moment when we do Docker build this, Docker build that, it's going to pull images from the hub and then packages, etc., and then the Wi-Fi is gonna die or burn or explode, and nobody wants that. So we are going to do everything on cloud instances on US East 2, because that will be easier. You need a little bit of Docker knowledge, but that's totally fine if you're not a Docker guru or anything. I'm trying to make this like accessible. All the code samples are super simple. The most complex service is probably 50 lines of code, including white space and comments. And the Docker files are also super simple so that it doesn't become like a blocker. If you want to redo that on your own, we have an environment for that as well. I will get to that in a minute. This is all hands-on. So you are invited to, but you don't have to, repeat what I will be doing on screen. And all the stuff that we have to do is identified with those gray rectangles like that. Those gray rectangles and the little squiggly thing here, which is supposed to be a keyboard because I'm really not a really graphic-oriented person. So those rectangles identify the exercises. So if you want to go over the hands-on parts later, you can just like zoom through the slides and just look at the gray rectangles, and that works. So the first thing that is suggested in this exercise is to go to container.training. And if I go to container.training, it will, and that's not a typo, by the way, that's really container.training. There is no .io, .com, etc. Just container.training. You get that page, which is also a good demonstration of the extent of my front-end skills. And I invite you to click on the second link, the one with devopsdays Minneapolis. It will send you to the full slide deck that you're seeing now, as you can see with the little 1/128 in the corner here. If you don't click on that link, but if you click on that link, then you get the full director cut verbose edition, which has almost 400 slides. Make sure you pick the right one, otherwise it will be weird. So the reason why we have the slides online is because sometimes if you're on the back of the room, or if your eyesight is not like eagle and everything, or if you are behind the pillar there, you might want to be able to see the slides anyway, so that's why they are available here. Okay, and the other thing is that I invite you to do is to join the conversation. If you click on that link here, it will send you to Gitter. Gitter is awesome because there is no registration to do. There is no, oh no, I already have 17 Slack teams. I don't want this to be the 18th, please. So Gitter is a very simple chat system. It's very ad hoc, I would say. And so if you go on Gitter here, and you just click on sign in with GitHub. Oh, now this is embarrassing. Okay, and so security is important. You should have 2FA. If you don't have 2FA, just stop everything you're doing right now and go implement 2FA. All right, and there we are. And in that chat room, Solshek is here. And so, yeah, just live from Berlin, we have a TA who will be able to answer your questions if you have questions during the workshop, because not all of us sometimes want to raise their hands in front of 90 people. So don't hesitate to use the chat room and to use and abuse it to ask questions, leave live feedback, like, oh, so slide 55 wasn't really clear to me, and whatever was next didn't explain it better. So yeah, don't hesitate, because I use this as a kind of collective scratchpad after to improve the material. All right. So I talked about a VM environment, so that's what those little pieces of paper are all about. Because during the workshop, we are going to experiment with a 5-nodes cluster. Everybody has a 5-nodes cluster somewhere on US East 2. And if you are doing this on your own later, you can use Play with Docker, which gives you like throwaway sandbox Docker nodes. But for today, we have these things. So everybody has 5 VMs. The VMs will be up until later tonight. And the first thing that we will do is to make sure that our VMs have been correctly deployed. So I'm going to SSH into my first VM. So here, well, I'm lying. I'm not going to SSH. I'm going to use Mosh because it will be slightly more resilient to network issues and whatnot. So if you know Mosh, the mobile shell, you can use it. Otherwise, SSH is just fine. It will behave exactly the same way. All right. And by the way, here, you should put the IP address on your piece of paper, not the IP address on screen. Otherwise, you will end up on my cluster, and then we won't be friends anymore. So once I'm here, I'm going to use tmux for reasons, and I'm going to check that I can SSH from one node to the other. My 5 nodes have DNS aliases, so I can do like SSH node 2, so it's node 1, 2, 3, 4, 5. And when I do SSH node 2, the first time I have to accept the key, and then boom, I get logged on node 2. Amazing. Now I can go back to node 1. And we will do almost everything on node 1. The only reason why we have SSH access to node 2, 3, 4, 5 is mostly for initial setup and then for debugging. But the code will be checked out on node 1. Node 1 will be our bastion host or command center or whatnot. Sometimes I will say, let's open a new terminal or let's open a new window. Here you can either like actually really open a new window and a new SSH connection, or you can use something like tmux or screen. So this is the option that I prefer personally, because with tmux you can do fancy stuff like splitting the screen and having multiple panes, etc., etc. And if, like me, you can never remember the keyboard shortcuts, I have a cheat sheet here. But this is not for you, because if you don't know how to use tmux, you should not start to use it now, because it's going to make everything even more complicated. So just have multiple windows in that case, pretty please. OK, so what do we have on these VMs? We have brand new versions of Docker. So Docker version is telling me that we have 1706. We have Docker Compose, and we have Docker Machine, and that's all we need. So now we are all set, and we can start to deploy containers and microservices and scale things. So first, the application that we will use as the example is in the same repo with the slides and everything. That repo is shown here. So that's on GitHub. Petazzoni, that's me, and Orchestration Workshop, because I'm not very good at naming things. And if I go to that repo, I see, well, first I'm going to tell you where the slides are hidden. It's in the docs directory, and then we have an index.html file here, which contains Markdown. I'm using Remark, which is an awesome piece of software so that you can write slides in Markdown and then show them in the browser. And this is the content that we are presenting right now. In fact, if you have a closer look, you will see that there are way, way, way more slides in this Markdown file, but they have tags depending on whether this is self-paced or in-person, or whether we want to do extra details, whether we want to do an extra chapter about logging, et cetera, et cetera. But anyway, if you're wondering, how can I change the slides? That's there. Same thing if you want to save the slides, et cetera, et cetera. It's everything in the repo, so you don't have to worry about that. Now, the demo app is in the Docker coins directory. We can know that this is a containerized application because there is a Docker Compose YAML file. A Docker Compose YAML file in Dockerlandia is a little bit like when you have a Vagrant file or a make file or package.json. When you see these files, you know that you can do Vagrant up for Vagrant file. If you see a configure script, you can do /configure make install. If you see a package.json, it means you probably can use npm install. Requirements.txt means you can use pip to install dependencies, et cetera, et cetera, et cetera. When you have a Docker Compose YAML file, it means, well, you can use Compose to bring up this application. So that's what we are going to do shortly. But first, we are going to look inside this Compose YAML file to see what it looks like and have an idea of what to expect. The Docker Compose YAML file lists a bunch of services, and for each service, I have either an image instruction, which means, all right, for the Redis service, I want to use the Redis image from the Docker Hub. So just pull that image from the hub and run it, and it will just run like a default Redis thing. The other services, Worker, WebUI, Hasher, RNG, I don't have an image instruction here. I have a build instruction. It means instead of pulling an image from the Docker Hub, I want you to build a custom image using whatever is in the corresponding directory. Again, I'm not I don't want to do fancy things when I name things. So the RNG service is in the RNG directory. The hasher service is in the hasher directory, and so on and so on. If I go to one of those directories, for instance, in hasher, I will see that I have a Docker file. So this Docker file will explain how to build that specific service, how to make the container image that we use for that service. And in that case, if you're familiar with Docker files, this is not surprising to you. Like there is from, run. If you don't know Docker files, this means we want to use a base image, which is like the Ruby image in the Alpine flavor. This is like a small, specificient image, which is based on the Alpine distro instead of, say, Debian or CentOS or whatever. Then we run a few commands to add, in that case, build base. So that's to add a compiler. And then we gem install Sinatra and Thin. We add some source code in the container. And then we say, when this container is started, we want to run ruby hasher.rb. OK, so that's build instructions for a container. So we have those 4 services, so 4 microservices, and I'm going to prove it because, as I said earlier, the source code is very, very trivial. Yep, it fits on the entire screen. It's 18 lines of code, including white space and comments. So again, super trivial examples because I don't want the code to be an obstacle when we work on this. And if you're already thinking, well, this is Ruby, I'm out, just stay 1 more minute, I have a surprise for you. So in this code, in this application, we are using the container way to discover services and talk to other containers, which is that in your code, instead of putting like an IP address or an FQDN and then having some config file on the side or whatever, you just put the name of the other service. I want to connect to Redis. Well, then, oh, by the way, worker is in Python, so Pythonistas, you can stay. And if you don't like either Python or Ruby, I also have other surprises for you, so please stay. So in the worker code, for instance, I say, OK, I want to connect to Redis. Fine, I just connect to Redis, which at first it's weird. Either I connect to 192.168.1.3, or maybe I connect to redis.awesomestartup.com or something like that. But Redis, what does that mean? Well, at some point, there will be some magic DNS thing that will automatically resolve Redis to the right thing. So don't worry about it. Same thing here when I want to talk to those web services, RNG and hasher. I just put http://RNG or http://hasher, and that will work. OK, so what exactly is this Docker Coins application? It's not exactly a cryptocurrency, unfortunately. You can't buy anything with Docker Coins, even if you have trillions of jillions of them. The Docker Coins code has only one common point with Bitcoins, is that it ends with coins, and it also eats lots of CPU cycles. So how it works is that there is a worker doing an infinite loop, and during this infinite loop, it's going to generate a random number, a random string of bytes. Then it's going to hash that string of bytes, and then it's going to repeat that again. Like generate random bytes, hash them, generate random bytes, hash them, and in a loop infinitely forever and ever and ever. And then every second, it will update a Redis counter to indicate how many loops it was able to do. Oh, I did like 7 iterations since last second, so I'm going to add +7 in the Redis counter. Oh, I did 25 iterations, so I'm going to add 25 to the Redis counter, and so on and so on and so on. And then there is a little web UI that will look at that Redis counter and that will graph a speed for us so that we can see how fast our Docker Coin mining rig is going. And that's pretty much it. That's all there is in this application. Now the twist is that the random byte generation thing is done by a web service. Instead of just calling like random.random or whatever, we call a web service to do that for us. And when we want to hash the data, we also call a web service to do that for us. So now we have tons of microservices that don't really serve any particular purpose except being very educational. All right, so first step is to run that on our node 1. So we are going to clone the repo. git clone, git colon / github.com. Is this big enough for everyone, by the way? Yep, no, maybe? Okay. /jpetazzo /orchestration workshop. All right. And then when I go in orchestration workshop, I can double check that, yes, indeed, that's really the repo I showed earlier. And if I go to the Docker coins directory, cool, I have my Docker compose YAML file, and I have the code for my microservices here. Perfect. Okay, so now we're going to do like the kind of knee-jerk reaction, which is, oh, we have a Docker compose YAML file, so we can do the magic command Docker compose up. And when I do that, Docker compose is going to parse the YAML file. It's going to say, OK, so you have a Redis service using the Redis image from the Docker Hub, so I'm going to pull that. Then you also have, right now it's pulling the Redis service. I see that you have the Hasher service. It's using the Ruby image, so it's pulling Ruby. Now it's installing packages on top of the Ruby-based images. Then it's going to gem install Sinatra and Thin. Then it's going to build native extension, which will take a while. I don't know why it says this could take a while. It always takes a while. After that, it's going to build the other services, and you will see that we have some Ruby, some Python, but also some Node.js. I didn't include Java, not because I don't like Java, but just because confession, if I want to include Java, I should probably learn one of the modern JVM-based languages to have something short and concise, and I didn't do that yet. All right, now that's the Node part. And now this is the output of our application. On the left side, we have what I call the rainbow, which is the name of the containers, each with a different color, hence the name rainbow. And on the right-hand side, that's the output of these containers. So the web services are super simple, and all they do is print like an Apache-style HTTP log. And then the worker is just printing some information. I'm going to freeze that with Control S. And I can see that Hasher and RNG. So I see like this, for instance. I see RNG Hasher, get for RNG. RNG standing for random number generator, right? And then the data that we got from RNG is sent to Hasher. So I have a post request to Hasher, and then another one to RNG, and then another one to Hasher, and so on and so on. And once in a while, every second or so, the worker will tell us that many units of work have been done, and I'm now updating the hash counter in Redis. And in that case, it's pretty steady. It's like 4 units per second, and it's updating every second to add 4 to the counter in Redis. All right. So by the way, this is like the easy win with Docker. It's like I didn't need to figure out, do I need to install Node and which version, and Python and which version, and whatever, and dependencies. I just did Docker compose up, and that just works. Those logs are not extremely exciting, so I'm going to hit Control C, where I'm hereby politely asking to compose to stop the application. We can see here that 2 containers are well behaved, and when we ask them politely, please quit, they do quit immediately. Hasher and Redis show like done immediately when I hit Control C. The 3 other containers, however, are not really paying attention. They don't exit immediately. It's only after 10 seconds that we see them exit. Why is that? Because when we stop the application, we send the term signal to all the containers. Some containers are well behaved, and they're like, oh, you're asking me to quit? Fine, let's do that immediately. Some containers just don't give anything about that and just continue to run. And in that case, after 10 seconds, Docker is like, well, I think I made a request 10 seconds ago. I think it was about you stopping whatever you were doing, and you're still doing the thing. So I'm going to send you a kill signal, which you can't stop, and then the container exits. This will be important a little bit later, because we will see that some containers take longer to restart and whatnot. It's all because whomever wrote this stupid application did not handle signals properly. Sue that guy. All right, so I'm going to restart the application, but in the background, because again, logs and rainbows are fine, but I don't really need to see that all day long. So I'm going to do docker, docker compose up -d, -d like demonized or detached. It's the same flag as for docker run. If you want to put something in the background, you do docker run -d. And now my containers are running in the background. If I do docker ps, I can see a bunch of containers running. I can also see a lot of information that requires a much wider terminal than I currently have. So it's a good idea to use docker compose ps instead of docker ps. Sorry, docker compose ps. It shows me a more concise list of containers with more useful information. And in particular, it will only show me the containers of this application. So if I'm running on a big cluster with thousands of apps, when I do docker compose ps, I see only the containers of my application instead of all the applications running there. Fine. So I mentioned the web UI, so we are going to look at that. So in my web browser here, I'm going to put the IP address of my node. So mine is 18.2.20.36.131 on port 8000. Why is it 8000? Where does that come from? It's all in the Docker Compose YAML file. Here, for web UI, I have a port section which says, I want to map port 8000 on my host to port 80 in the container. And that's my web UI. We can see that we are doing kind of 4 hashes per second. I say kind of because it's not exactly 4 hashes per second. It's more like 4440, 4440, etc., etc., etc. But that's my mining speed. Okay. So the goal is to make that graph go up and up and up, and without changing a line of code, because otherwise we could just cheat and replace the whole worker by something that just increments the counter in Redis, and then that would be great. But no, the contract is we cannot change a single line of code in the Python, Node, and Ruby apps. We can change whatever we want around that, like the Docker files if needed, or the compose file, or the infrastructure around it, but we cannot touch the code. Okay, so first let's try to find out what's the bottleneck. Like, am I lacking CPU or memory or whatever? So I'm going to use some good old Unix tools like top, and top will tell me that there is a suspicious Python process using 1% of CPU, and also a bunch of suspicious processes using less than 1% CPU. But overall, the machine is doing 98% nothing. The machine is idle at 98%, so I have plenty of CPU available. Same thing if I look at the memory with like free, it's telling me that this machine has 4 gigs of RAM and 2 gigs are entirely free, untouched. So I have plenty of memory. All right, let's get the big guns. Let's use Vmstat. And Vmstat is going to tell us that we are not swapping in or out. We have virtually 0 block in, block out activity. That's the BI, BO columns. And everything else is kind of normal. Trust me on this, like the other parameters are okay. This is just like in the hospital shows when they tell you like all like numbers and everything, and you're like, does that mean it's gonna die, or does that mean it's gonna be okay? In that case, everything is fine. This machine is doing nothing. Okay, so how can we use these extra resources? Well, since the only thing that's kind of driving all the work is the worker here, so we are going to clone that container. Instead of having one worker doing like get random data, post random data, increment counter, get random data, post random data, increment counter, we are going to have multiple workers doing that in parallel, and that should work. And we're lucky because in Compose there is a very simple scaling function that we just clone containers. So I can do docker compose scale worker equal to. So when I do that, it's just creating another perfectly identical container. And if I look at my web UI here, instantly I see that instead of doing 4-ish hashes per second, I'm doing 8-ish hashes per second, which seems promising. And so I'm going to like continue on that, like, let's say, good trend or something. If I scale to 3, yep, it's going up. That's wonderful. Let's scale to 20 immediately. And it doesn't work. We're kind of stuck at 10 hashes per second. And that's a good thing, otherwise there would be no point in the whole workshop. So we are stuck at 10 hashes per second, and we're like, okay, what's going on now? Okay, let's look again at top. And if I look again at top, I see that now I have a bunch of suspicious Python processes, but the machine is still idle at 96%. If I look at the free memory, now instead of 2 free gigs, I have 1.7 free gigs. And if I look at Vmstat again, I still see nothing at all. So I still have plenty of resources available, and I can wonder what the heck is going on here. So what's going on? Well, something is slowing us down. What could it be? Normally, we all have like some crazy sophisticated instrumentation like Datadog and like New Relic and whatnot. But here, we are in simple land, and so we don't have these things. So we are going to use really, again, old school web services diagnostic tools. If I look in my compose file, I see that the RNG and hasher services are exposed on ports 8001 and 8002 on my machine. And I can see that here if I do, for instance, curl localhost 8001, and it will tell me, hello, this is RNG, and I'm running. Same thing if I do that on 8002. Okay, so I'm going to use HTTPing. HTTPing is exactly like ping, except that instead of throwing ICMP packets at the target, it's just going to do HTTP requests and time them to see how fast or how slow the web server is. And if I do HTTPing on localhost 8001, I see like 1.7, 1.8 seconds of response time. For a service on localhost, this is bad. And just in case you're not convinced about it, I'm going to do the same thing on the other service, the one on port 8002. And yeah, that one answers in 1 millisecond, which is way more consistent with the usual performance characteristics of the loopback interface on Unix systems. So why is that? Well, we don't know exactly, but what we can say is that apparently the problem is with the service on port 8001. That one seems to be slower as we scale up and down. And which service is on port 8001 again? That's RNG. And so at that point, we are going to summon that annoying person who always knows everything about everything, and we will say, yep, I know what's going on here. It's because of entropy. So like, what's entropy? And yeah, it's because when you want to generate random numbers on Linux, you need to get that randomness from the entropy pool. And it's impossible with a computer to generate random numbers because I mean, the computer needs to get that from somewhere, and it can't. So instead, it's going to use external information, like the timing between 2 packets on the network interface, the timing between keystrokes, things like that, that normally should be random enough. Or it will have an internal like temperature sensor, and it will look at maybe the tenth digit after the decimal point for the temperature, because that should be random enough. So you need that entropy thing. You need to have that entropy pool. And if you need too much random data, then you drain and empty the entropy pool. And then the next time you need a random number, instead of getting that number right away, the program kind of stops a little bit and then gives you a random number next time there is a packet on the network interface, something like that. If you have generated like PGP keys or things like that, you might remember when you generate your keys, it's telling you, now please move the mouse so I can get entropy. And you're like, what? So that's exactly what it's doing. It's going to use like some random information, like the timing between the interruptions to get that entropy. Okay, that sounds like reasonable. It's complete bullshit because the code of the RNG service is not using that entropy pool. It's not using /dev/random, which exhibits this behavior. It's using /dev/urandom, which does not have this problem. But we will still buy this bullshit because it gives us a nice excuse to scale out our service on a cluster. And without scaling out, there would be no fun. So before moving on, we are going to shut down like this single node application with Docker Compose down. And again, Hasher and Redis are well behaved and they stop immediately. And everybody else is lagging behind and will be killed after 10 seconds. There we are. Thank you. OK. So we need to scale out. I'm going to check on the chat if there was like questions or anything. That's what's hidden behind that podium. Well, this thing disconnected from the Wi-Fi. So to scale out, we are going, well, maybe I can, like if there are like some hand-raising questions or something. No? So far, so good? Is everybody still alive? Yes? OK. Nope. So to scale out, we are going to use SwarmKit. SwarmKit is initially a toolkit, a library to build distributed multi-node systems. Maybe something that would be pretty close to SwarmKit would be Nomad from HashiCorp, in the sense that SwarmKit was designed and built to do one thing and do it well. And then it was bundled with Docker so that it's easier to use. It's a reusable library, so you can like take that and build something completely different with no containers or anything whatsoever. But here we are going to use it within the Docker engine. So what do we have in SwarmKit? Well, first of all, observation. Each time we have some kind of distributed system, we need to have a source of truth, like some place where we keep the family jewel, the crown's jewel, the important stuff that if we lose it, then the cluster is gone and there is no point and we can stop and everybody go home. So often if you look at systems like Mesos, you will see, oh, there is a zookeeper somewhere. If you look at Kubernetes, there is etcd. Et cetera, et cetera. And so here, OK, we need a system like that, but we are going to embed it in SwarmKit instead of having a dependency on something external. That's the same approach in Nomad, by the way. It's using Raft and Surf, I think, internally. OK, so we have a highly available distributed store embedded in SwarmKit to store the important data that we absolutely don't want to lose, like what are my nodes and what are the keys that I need for these nodes to communicate, et cetera, et cetera. Another thing on the spec sheet was we want to be able to reconfigure that dynamically without any problem. This came from PTSD from administering Zookeeper clusters. Zookeeper is solid. Like you can like shoot at it and you can do horrible things to your cluster and it's going to survive. However, when you want to add or remove nodes to the cluster, like, oh, I had 3 nodes and now I want 5, or I want to go from 7 to 5, or I want to move one node to something else, these operations are not easy. And in the case of SwarmKit, we said, OK, we want these things to be so easy that you can do them at 3 in the morning after a few too many glasses because you need to. We also wanted, no, that's it, I just said it, dynamic reconfiguration. So SwarmKit provides services managed with the Declarative Api. So here, it's useful to contrast between an imperative API and a declarative API. The imperative API, that's the one that we use with Docker run, for instance. Like, oh, I want to start a container. I want to start another container. I want to stop that one. You give instructions, but if something happens to your containers, it's your job to kind of revisit again, check what's running. Like, for instance, if you want 4 web front ends, you have to do Docker run 4 times, and then you have to check once in a while. And if at some point you're like, oh, crap, there is only, I only have 3 front ends now, then you have to manually start another front end. That's imperative API. Now, declarative API is when you say, I want 4 instances of that thing to be running at all time. Make it happen. So you say what you want to have, and the system will make it happen. It will be the system's responsibility to do that kind of watch loop where it permanently checks, oh, you wanted to have 4 instances, I will make sure you have 4 instances. Oops, we lost a node, so now we have 3 instances. I'm going to take care of automatically adding the 4th instance that we need. Oops, in fact, it was just a network split, and now the node is back, and now we have 5 instances. That's okay. I'm going to terminate one of the 5 instances so that the actual state matches the desired states. And we call that the reconciliation loop, where the system is just comparing like what we want and what we have, and it's making adjustments. In addition to that, SwarmKit integrates with overlay networks, which is a construct to give private networks for groups of containers, and load balancing and service discovery. And it also has a really strong emphasis on security. So for instance, there is automatic TLS keying and signing with cert rotation. And plus like, this is basically supposed to be security person wet dream of all the things you want to have in a solid system. The data plane, so the communication between the nodes is fully encrypted. Sorry, that's not correct. It's the control plane is fully encrypted. The data plane can be easily encrypted, but is not by default. And there is also automated key rotation, so that each time you have a new connection between 2 nodes, they negotiate a new key. Every 12 hours, they renew those keys. And for the certificates, it's every 3 months. And it has a least privilege architecture, where the idea is it's a little bit like in MI6 or the CIA or stuff like that, where each node knows just what it needs to do its job and nothing more. So that if a node is taken by the enemy forces, you can be sure that it won't admit anything under the question that it shouldn't tell. More seriously, though, in the context of clusters, it means that if somebody manages to hack into a node because those pesky marketing people deployed a WordPress 6 months ago and never updated it, and eventually those pesky ops people never updated the kernels, and now we have a full-on node escalation, and now we have some hostile Russian hackers having root access on the node. Well, with the least privilege architecture, those people just have access to this node and the applications on it, but not to the rest of the cluster. And that's pretty important. And last but not least, there is full on-disk encryption, so that if people manage to steal your backups or your disks or sniff your fiber channel or EBS or whatever connection, they won't be able to learn anything about your cluster. All right. Now, more practically speaking, in SwarmKit, we have the notion of a cluster, which should be at least 1 node, preferably more, but you can have just 1 node. It's okay. Like if you want, you can have a 1-node cluster locally for development and testing. A node can be either a manager or a worker. Both kinds of nodes will run containers if you want to, but the managers are taking an active role in the Raft protocol, which is used to store all the important data, the highly available key value store. You can talk to managers using the SwarmKit API. So that's how you say, I want 5 copies of this service up and running. This happens by talking to the managers. One of the managers will be elected as the leader. This happens automatically. And if the leader goes away, there is automatically a new leader election, etc. And the other managers are just forwarding requests to that node. So when you talk to a manager, if you talk to the leader, then it will execute what you're asking the manager to do. If you talk to a non-leader node, like you talk to a manager, but it's a follower manager, it will transparently forward your request to the leader. And for you, it will be the same thing, except your request has been forwarded. And the workers get all their instructions from the managers. Since this can be a little bit confusing, I tried to make a little illustration where all the cute blue whales are nodes, workers, and managers. The managers are the monkeys, and the gray monkeys are the followers, and the pink monkey is the leader, and the dotted triangle here is the Raft protocol. So if I want to start a service running across multiple nodes, I talk to one of the managers, any of them, and if I'm talking to the purple manager, it's going to do what's needed. If I talk to a gray monkey, it's going to forward the request to the leader. Okay. More concepts. So with that SwarmKit API, I can ask to run services. I can see the state of the cluster. I can have a bunch of things to act on the cluster. And services, so the things that I want to run on my clusters, are defined a little bit like when you do a Docker run command. So when I want to create a service, I have to say which image I want to use. Maybe I want to give a special command or some arguments, environment variables, labels, et cetera, et cetera. And I indicate how many instances if I want that service to be replicated. And then that request ends up on the leader inbox, so to speak, and the leader will break that down in multiple tasks and push those tasks to the node so that they can run them. I'm not going to give like too much details about how exactly that works, but if you're curious, feel free to ask me after. So now, this is SwarmKit, but since Docker 1.12, so June 2016, SwarmKit is embedded in Docker, but it's sleeping by default. All that code is kind of dead or sleeping or inactive, and to make it active, you have to enable Swarm mode. And once you enable Swarm mode, then a bunch of Swarm-specific commands are available. So for instance, the Docker service command to manage services, as long as you have not enabled Swarm mode, it will tell you, nope, you need to enable Swarm mode. Same thing for Docker node to list the nodes in your cluster, et cetera, et cetera. Okay, so example, if I do Docker node ls, it's telling me, nope, this is not a Swarm manager, go away. So I need to do Docker swarm init to enable Swarm mode. And when I do that, then that's it. Now I have transformed my isolated Docker engine into a one node cluster. And now if I do Docker node ls, it's going to tell me, yep, that's the list of nodes in your cluster. There is only one of them so far, but it's a pretty good start. Okay. So a token was generated, and there again, I'm going to skip exactly what that token is, but feel free to ask later. And now we are going to add more nodes to the cluster because a one-node cluster is not very exciting. So to add nodes to the cluster, we need the command that was shown to us when you did Docker swarm init. Here it tells us, hey, if you want to add nodes to that swarm, you need to run that command on these nodes. And if you lose that command, don't worry, you can see it again by doing Docker swarm join token walker. Okay, so I'm going to log into another node, like node 2, and copy paste that command. And it tells me this node joined a swarm as a worker. And that's it. Now I have a two nodes cluster. And I'm going to prove it by doing Docker node ls, which on node 2 will not work because node 2 is not a manager, it's a worker. And workers don't know anything, they just know about themselves. A worker doesn't even know the list of the other nodes making the cluster. So the worker has no idea if this is a 2 nodes cluster or a 2 million nodes cluster. It doesn't know. If I want to see the list of nodes, I have to go back to node 1. And now if I do Docker node ls, I have a list of 2 nodes. Okay, fine. Now we are going to add more nodes. But we are going to add manager nodes for redundancy, because at this point, if I lose node 1, then my cluster is completely dead, and I will have to go through really annoying recovery steps to make it work again. So we could like manually SSH to node 3, 4, 5 and copy paste, but no, that's too repetitive and that leads to stress. So instead, we are going to use the shell, not that shell, but another shell. So first, I'm going to get the token for my cluster. So that's with Docker swarm join token -q manager. So here, I'm asking for the manager token, and -q means, hey, don't show me the whole command. I just want that token, and this is my token now. I'm going to put that in an environment variable. And then I'm going to loop over the other nodes. So for node in node 3, node 4, node 5, do SSH $node, and I want to do docker swarm join -- token $token. And then I have to tell it, okay, which node do I want to connect to? Like a seed node, where is the cluster I want to join? Well, node 1 colon 2377. What is this 2377? It's just a default port for intra-cluster communication. 2375 is the Docker API port. 2376 is Docker API port with TLS certificates, and 2377 is for swarm communication. All right, and then I do done. It's going to SSH over the 3 nodes. I just have to confirm each time, yes, I really want to accept the key of that node. And that's it. Now if I do docker node ls, I see that I have a 5 nodes cluster. Okay, so quick check, who got their 5 nodes cluster up and running? That's a bunch of people. Who did not get it running? More people. Is it because I'm going too fast or because something went wrong? Okay. So we got a 5 nodes cluster. I'm going to skip the whole business about like promotion and demotion of nodes, and also the thing about how many managers do we need. This is just about quorum. I will there's a really frequently asked question, which is why can't I just have all nodes be managers? That would be simpler, right? Well, not quite, because the Raft protocol is such that when you write to Raft, you need to write to all the nodes. So if all the nodes are managers, when you update something, like when you create a service or when you update it, or even just like when a node joins, then you need to send the write to all the nodes in the cluster. If you have a 1,000 nodes cluster, it means that every single change will be like 1,000 writes, so 1,000 packets going out of a machine, and then the acknowledgement, and etc. So that would be pretty bad. So instead, you want to have a small subset of nodes be your managers. So how do we, like in the real world, how do we deploy a Swarm cluster? Well, we can use the method that we just saw and run commands manually or SSH. Don't do that. I'm kidding. You can use your favorite configuration management tool. There are like recipes using Puppet, Chef, Salt, Ansible to do that. The general idea is always to have a seed node, and then you expose like the tokens somehow in the facts of your cluster, and then you push that to the other nodes so that they can join. There are also special, like we call Docker editions, like Docker for AWS and Docker for Azure, which are easier to operate and maintain. And so in the slides, I have links directly to that. And the idea is that on AWS, it's using CloudFormation templates, and you end up with 2 nice auto-scaling groups, one for the managers, one for the workers, etc. And it's like beautiful and best practice, etc. On Azure, I don't know exactly how it works, but same idea, I suppose. OK, we have a Swarm cluster. So now let's abuse it and start services on it. The general idea is that if you know how to start containers with Docker, you just have to mentally replace Docker run with Docker service create. So for instance, I can do, instead of Docker run alpine ping goo.gl, I can do Docker service run alpine ping goo.gl. Oops, Docker service create, sorry. Docker service create, and then the image name, and then the arguments. And when I do that, it's giving me the ID of the service that I just created. OK. And I can use Docker service PS on this ID, either by copy pasting or just typing the first letters of this ID. And it's telling me that I have one container running on some node somewhere, and it's been started like 20 seconds ago. Okay, fine. So now I have a container somewhere pinging the go.gl shortener service. Okay. There was like an interesting warning message about -- detach. Let's ignore it for now. We're going to revisit that in a minute. How can I see the logs of this service? Well, with the docker service logs command. So I just do docker service logs, and then I put the ID of the service, or just the first few letters, and I see like the output of the ping command. And again, I have like the output is in two parts. On the left side, I have what is in fact the full container ID. It's telling me which container it is and which node. And on the right-hand side, I have the output of the container. So in that case, the result of the ping command. Okay, great. Now let's scale this. We need more pingers. So I'm going to update the definition of that service. I'm going to say, you know what, instead of one copy of that container, I want multiple copies. So I do docker service update for that. So docker service update. My service was TB something whatever, I think. Let me check. I forgot already. Yes. Docker service update, TB3, -- replicas 10. So supposedly now I have 10 containers pinging go.gl. Let's look at the logs again. And I'm going to add here like, whoops, to the docker service logs command like -- follow, which is the equivalent of -f when you use tail -f. So now I have the logs streaming here. And yeah, I see that I have a bunch of containers now busy pinging go.gl. And right now there is somebody at Google wondering why the heck there are like hundreds and hundreds of ICMP packets going to the servers. And it's not the first time that it happens. It's always from some EC2 region, and it just lasts a few minutes and then it stops. And I'm sure that this person is really wondering what's going on. Maybe I should tell them someday. What about that -- detach flag? So this is so you can use asynchronous or synchronous updates. You can say, hey, instead of immediately exiting to the command line, I want you to tell me what's going on with this service update command. So I can do, for instance, docker service update, TB3, -- replicas 15, -- detach equal false. And now it's going to tell me exactly what's going on. And then after, it's just waiting a few extra seconds to make sure that all my containers are up, running, and stable. If they were like constantly crashing and restarting, this would wait. Okay. How do we expose a service now? So how do I, instead of just doing distributed ICMP packets, I want to have an actual service exposing like a TCP socket. And in my example, I'm going to use Elasticsearch. So I'm going to create a service, docker service create. I'm going to name it so that I don't have to put like TB3 whatever when I reference it. I can use its name. So -- name search. -p is the flag to publish a service. Just like docker run -p, we have docker service create -p. And I want to expose 9200 because that's the default port for the Elasticsearch API. What else do I need? I want to have, straight out of the box, I want 7 replicas. So instead of saying just start 1 copy, it's going to immediately start 7 copies of Elasticsearch. And I want -- detach equal false. And I want the image Elasticsearch :2. Why Elasticsearch :2 instead of just Elasticsearch? That's because the latest version of Elasticsearch absolutely wants you to provide a configuration file. It will refuse to start if you don't provide a config file. I don't want to be bothered with configuration files, and nobody got time for that. So instead, I'm just using an older version that will just start without a configuration file. So when I do that, now I can see the state of my task. So first, it's preparing, which means I'm pulling the image, I'm connecting to networks, I'm doing all the plumbing that is necessary, and then starting, and then running, and then it's going to wait 5 seconds to make sure that stuff is really running and not just like stuck in an endless restart loop. Okay. So now I have 7 copies of Elasticsearch running on my cluster. How do I check if they are really up and running? Well, I exposed them on port 9200, so I can do curl localhost :9200, and then I will see this is the default route for Elasticsearch. If you've already used Elasticsearch, you've seen that before. Otherwise, like this is what you get when you just hit Elasticsearch like that. Why did I use Elasticsearch? Because it generates a random name that you can see here, like cardinal. So if I do curl multiple times, I will get a different name, and then another, and then another, and another, and at some point, it will loop again on the first name. And to illustrate that, I'm going to use JQ like this, and I'm going to do a for loop, like for x in sec110, do this. So if I do 10 requests to my Elasticsearch service, I see that the requests are served by like 1, 2, 3, 4, 5, 6, 7, and then it loops back to the beginning. So in fact, on port 9200, I don't have directly my Elasticsearch service. I have a load balancer that will do a round robin on the request and serve them to the backends of my service. Okay, so we have load balancing. All right, let's skip the details on the TCP routing mesh. Visualizing container placement, we can skip that as well. I will maybe show it at the end if we have some time. Okay, so I show like the basics. How do I start a service, scale it? Now, how do I expose something on a TCP port? And there is like out-of-the-box load balancing. Okay, now we want to do that, but for the Docker Coins application instead of just one single standalone service. So first, I'm going to wipe out all the containers to have a clean slate. So how do I do that? Well, first of all, I'm going to list all the services with Docker service ls. I'm going to add the -q flag, which means just show me the IDs of those services. I don't want to have like the details about replicas and whatnot. All right, these are the IDs of my services. Fair enough. Now I'm going to pass those IDs as arguments to the Docker service rm command. So pipe xargs Docker service rm. And when I do that, it will execute Docker service rm with the arguments that are here. So it will basically, like this command here, like that's the swampapocalypse. It will destroy all the services on the Swarm cluster. Don't do that on production on your first day. I mean, normally you shouldn't have production access on the whole cluster on your first day, but who knows. Okay, and I just killed all the services. Great. So now it's time to run our app on Swarm. And I sped up a little bit before because I wanted to make sure I had enough time for this. But I will now try to have a more sensible pace. So this is where we are going to explain the whole build, ship, and run Docker motto. So we will build images for the Docker Coins app. Then we will ship those images. We will put them somewhere so that they are available to all the nodes. And then we will run services with these images. So why do we need to ship the images? Because if we go back to the very beginning, when we did Docker Compose up, we did the build part, we did the run part, and we didn't need no ship part. So why do we need to ship now? Well, because when we did Docker Compose up, that was on a single node. So we built on a node, and then we ran on that node. There was never the need to ship, because you don't need to ship to yourself. So now we have multiple nodes, and we are going to build somewhere and then run potentially elsewhere. So we need to ship between the nodes. So that's why we have a ship step now. OK. The easiest way to ship stuff with Docker today is to use a registry. The registry is, I mean, you could imagine that conceptually a little bit as an S3 bucket or an FTP server if you are as old as I am. So it's just a big kind of a bit repository of thing, and you can put Docker images there. But it's using a fancy protocol that will let Docker know, OK, so you want the, let's say, the Redis image. It's made of layers, and you can pull those layers independently. Oh, OK, your hasher image is also made of layers, and now it starts making sense and being useful, because when you update your hasher image, instead of having to repush the whole entire image to all nodes, we can only push the parts that have been changed. And maybe your image is, let's say, 150 megs for the base stuff and Ruby and whatnot, but the code itself will be definitely less than 1 meg. So instead of pushing 150 megs to the whole cluster, you're just pushing less than 1 megs when you roll out a new version. So that's why it's nice to have this custom registry protocol. So we're going to use a registry. So the plan here is to build on node 1, because that's our control node. Then we are going to tag the images so that we say, OK, we want to push them to a registry. Then we push them to that registry, and then we create services referencing those images on the registry. Because when you reference images on a registry, Docker will automatically pull them. What I mean by that, if you do, for instance, Docker run 1234:8000 / blah, 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 Docker is going to try to connect to 1234 on port 8000, and it's going to try to get blah, 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 blah. And if I do that, yeah, now my Docker engine is busy trying to something that will never reply, and it's going to be very sad and lonely. But here, what we're going to do is, as a registry address, we are going to use localhost 5000 / some name. And why is that? Because we are going to run a registry locally, and we are going to expose it on port 5000. Remember when I had my Elasticsearch service, I could reference it with localhost :9200, and I could do that on any node, because on any node, I have a little load balancer that will spread my traffic to all the backends for my Elasticsearch service. So now we are going to do the same thing with the registry. The registry will be exposed on port 5000, which means that I can go to any node on my cluster, I can connect to port 5000, and I will be routed to the actual registry container. It's a little bit like a load balancer, but the other way around. It's more like a traffic director. Like I have many people connecting to it, and it's just sending to the right backend, and there is only one backend. Right. So to make that easier, yeah, when we do the long version of the workshop, we do like manually Docker service create for all the services one by one, so that we can really see how it works. Here, I want to show directly how we can leverage Compose to achieve that. And I'm going to show what it looks like, and then explain after, like break down the different steps. First, the Compose file can be used to describe services, just like a Compose file can be used to describe an application. The Compose file that we had in the beginning here, this Compose file describes my Docker Coins application. And this Compose file can be used to describe services as well. And the only thing we have to do, well, almost the only thing we have to do, is to bump up the version number here Sorry, to bump up the version number here and add a little bit of deployment information in that file. So first of all, if we wanted to deploy a registry on our cluster, we could run that command, docker service create, so far so good. So -- publish 5000:5000. So that means I want to map port 5000 on my cluster to port 5000 in my containers. Registry:2, and that's the image I want to run. When you want to run a registry, you can just use the official registry image. And by the way, that official registry image, registry:2, is the same image that powers the Docker Hub, that powers DTR, the commercial Docker trusted registry. The only difference is that there are extra plugins and like authentication front ends, etc. But otherwise, the part actually moving the bits around is exactly the same. It's an open source component. So we could create that registry with that command, or we could use a compose file v3, which looks at this point exactly like a compose file v2, where I say, I want a registry service using the registry:2 image and exposing the following ports. And that's it. And now to deploy that, instead of doing docker compose up, we use docker stack deploy. So I'm going to run the registry like that. So the stack files that I use for deployments are in the stacks directory in the GitHub repo. And so for registry, it looks exactly like what I have on the slides. And I do docker stack deploy. I give the name of the stack, let's say registry, and then -c, which is shorthand for -- compose file, registry.yaml. So when I do that, it's going to do something very similar to docker compose up, except that instead of creating standalone plain containers, it's running services. So now if I do docker service ls, I see that I have a service named registry_registry that is up and running on my cluster. Why registry_registry? The first registry is the name of the stack. The second registry is the name of the service in the stack. So that registry here corresponds to the name I gave there, and that registry here corresponds to the name in the YAML file there. Okay, so now I have a registry running on my cluster, and indeed, if I do curl localhost 5000/v2/_catalog, that's just one of the API endpoints of the registry, so it's a good way to know if it's running. It tells me what images are present on the registry. And in that case, there are no images because that's a brand new registry, it's empty. So it's telling me repositories, nothing. Let's check that it's actually working. I'm going to pull like one of the smallest images you can imagine, the BusyBox image. And I'm going to re-tag it. So docker tag BusyBox, localhost 5000/BusyBox. So I'm just adding a new bookmark, if you will, pointing to that same BusyBox repo, and that bookmark is named localhost 5000/BusyBox. And now if I docker push localhost 5000/BusyBox, it's going to parse that name and say, oh, okay, so you want to push that image and you want to push it to localhost 5000. Fine, let's do that. Okay, and that's it. It was super fast because BusyBox is tiny. And to prove that yes, indeed, I've really pushed something to my local registry, I'm going to do the same curl command, so curl localhost 5000/v2/_catalog. And now in the list of images, I have the BusyBox image. Right, so at this point, we have a self-hosted registry. I don't know on which host it's running, and I don't care, because I can go to any host. I can talk to localhost 5000, and there will be a little load balancer that will send me to the actual container, regardless of its actual location. Okay. Testing the registry, pushing an image, checking what's on the local registry. Perfect. So now, how are we going to make the build and ship part easy? That's where we're going to do some small modifications to the compose file. Let's look. So here, in this compose file extract, instead of having just image or just build, I have both. So in a compose file v2, that makes no sense at all. Like either you build or you use an image from the hub, but you can have both. In a compose file v3, and that's why there was a v3, because something that was nonsensical before now makes sense. In the v3, this means we want to build that container image using whatever is in the www directory, and we want to name the resulting image like this. So in that case, we want to name it myregistry.company.net:5000/webfront. So that means that when I build with Compose, then my images will be named in a way that is ready to be pushed on my company's registry. So let's try this. So I'm going to do docker compose -f. So what is this -f flag? This flag means, hey, instead of using the docker compose YAML file, I want to use a different file. So in that case, I want to use dockercoins.yaml. Build. The build was almost instantaneous because this is the exact same Docker coins as we built like half an hour ago. So it's all cached and fast. And now I'm going to do docker compose -f dockercoins YAML push. And it's going to push to my local registry. And while it's doing that, I'm going to have a look at this. Yeah, I have it in the slides. I'm going to have a look at this YAML file to find out, okay, how does it know where it should push my image? How does it know that my registry is on localhost 5000? Well, there is no magic. If we look at the dockercoins YAML file, it looks just like the previous dockercoins file that we had, except that for each service now, we have this image line, which at first looks like it's something of the nature of nightmares because there is like $registry minus something, etc. What is that? In fact, this is using standard shell substitution with default syntax. This means the image should be $registry/RNG:$tag. But if $registry is not defined, I want you to use a default value, and that default value should be 127.001:5000. Likewise, we should use $tag, but if tag is not set, then I want to use a default value, which is latest, which is the default tag in Dockerland. So this means if I don't set anything in my environment, all my images will be localhost 5000/RNG:\latest, localhost 5000/worker:\latest, and so on and so on. But if for some reason I want to use a different registry, I just have to set the registry environment variable. If I want to use a different tag, same thing. I just set export tag equal blah, and I build and I push, and that's it. So with that tiny change in Docker files, now you make the Docker file like ship ready, so to speak. Okay, and so meanwhile, the push to the local registry is complete. By the way, if I repeat my curl command, now I see that I have a bunch of other images in my local registry. Great. All right, so the last step is the ship and run part. So it's the deployment of that stack. And we are going to use the same command as before, docker stack deploy. We are going to give a name to that stack, Docker coins. And I want to use -c, which again indicates which compose file to use, dockercoins.yaml. Okay. And now if I go to my web UI, so this is still the web UI of earlier, but now, boom, it's up and running. And I just have to give it, let's hit reload because. And that's my Docker Coins app running on a whole cluster, scaled across that cluster. And you can see on the y-axis that instead of being stuck at 10 hashes per second, we are happily going to 25 to 30 hashes per second. If we have a deeper look at the Docker Const YAML file, we see that for the RNG service, we have a deploy key that says mode global. This means that RNG service, I want it to be scaled in such a way that there is one instance on each node of my cluster so that I can better use that entropy. If we look at the worker service, in deploy, I have replicas colon 10, which means by default, instead of one single instance, I want 10 instances. And that's pretty much it. And this compose file can still be used in development. I can still use it with compose. The only thing is that when you feed that compose file into Docker stack deploy, it's giving you a small warning to say, I don't know what you mean with that build command, because the build command doesn't make sense for Docker stack deploy. Conversely, when you feed that compose YAML file to compose itself, it says, I don't know what you mean with that deploy command, because that doesn't make sense for compose itself. So we have a single file that can be used both for the development environment and the production environment, and with just like sections that are specific to each environment. So basically, you end up having a single source of truth. If at some point your application grows, instead of 5 tiny microservices, you have hundreds of them. In that case, you can break down the application in multiple compose files. And when you set the compose file, either with -f or with the compose file environment variable, you can specify multiple files separated, I think it's with colons on Unix and maybe semicolons on Windows or something like that. And basically, they will be concatenated. And the point of this is that if you have hundreds and hundreds of microservices, they typically make up like multiple big subsystems in your application. And what you will typically do is that for each subsystem, you will have a YAML file describing the let's say the production-like version, and maybe a YAML file giving a simplified mock version. So for instance, maybe in one case you have the actual Oracle database with all its bells and whistles, and the other case you have something that just mocks it so that you don't have to spin up a whole Oracle database when you're just running something in a completely different area of the application. And then basically you can imagine that you have a huge switchboard, and for each big subsystem of the application, you can select, do I want the production version or do I want the mock simplified testing version? Okay, so we've seen how to set up Swarm, how to host a registry, how to build container images, how to push that to the registry, how to deploy on the cluster, and how we could use Compose to go from dev to prod. That's great, but before we wrap up, I would like to show how we update services. Because often the demo stops here and like, okay, we can deploy, and I know that I went like pretty fast, I know that. But I mean, imagine if we do that like on a slower pace, and at that point everybody's like, okay, we got that thing up and running, that's great. But there is often the big question, okay, how do I make changes to my code, and how do I take those changes to production? Because at this point, well, I can create a brand new cluster and deploy it there maybe, but how do I make a nice change? Well, it's actually pretty easy. We are going to do that on the web UI. What we want to do is change like this, the size of this label here, because it's too small. So we are going to edit the file. So that's in web UI, where is it? Docker Coins, web UI, files, index.html. And in that file, somewhere there is font size 15px. I'm going to bump that to 45. I'm also going to maybe put font weight bold, just for fun. And I'm going to save and exit. And then I'm going to do again my build, ship, and run steps. So docker compose -f dockercoins.yml build. Then docker compose -f dockercoins.yml push. And finally, docker stack deploy dockercoins -c dockercoins.yml. Okay. Now if I do docker service ps dockercoins web UI, I'm just waiting for that to be deployed. Yep, done, okay. That's where the whole story about it take 10 seconds to the service to be restarted is important, because if immediately after doing docker stack deploy, if I had been like reload on the web UI, we wouldn't have seen a change, because the old service was still shutting down. So we would have to wait 10 seconds until the old service is shut down and then the new service takes its place. But now if I hit reload, I can see huge text here. So that's how I made a change, made new images, pushed them, redeployed them. Now, rolling updates. So this will be almost like desperately simple. The instructions are very similar, except this time we are going to change something in the worker. So I'm going to edit dockercoins /worker py. And here I have a sleep instruction. And by the way, if you wonder why we have sleep instructions in this code, tons of reasons. First, it's to achieve like consistent speeds. That's why the speed is so regular and everything. It's because the speed is not determined by our CPUs or network or whatever. It's determined by these sleep instructions. So it's mostly educational value. So anyway, I'm going to change that value here so that it sleeps 1 second. And then I'm doing the whole cycle again. But before, I want to show exactly what's going on. I want to run this. So this command, I'm just like explaining quickly that, oh no, I'm going to unzoom a little bit. This command just shows my 10 workers. It's fine if you can't see the fine print, because as you will see in a few seconds, we don't need to read the text. And now I'm going to do exactly the 3 same steps as earlier. So docker compose build, then docker compose push, and docker stack deploy. And when I do that, now what we can see is that here I have one service being updated. So one is shut down, the other one is ready. After 10 seconds, the old one is killed, the new one gets promoted, and then it's going to process another worker. So we're waiting for that one to be shut down, and after 10 seconds, it's going to be killed. And it goes to the next one, and so on and so on. So it's by default doing a rolling update. If I'm in a hurry and I want that rolling update to be faster, that's fine. I can do docker service update dockercoins worker -- update parallelism, let's say 3. Whoops. And then if I unzoom again, now you can see that there are 3 workers being updated at the same time. This can be done with the command line, but this can also be done in the compose file like this. In the deploy section, you can have like update config, I want this level of parallelism, and delay indicates how long you want to wait between 2 batches. If your services need some time to warm up and you don't want to just restart everything too fast. Okay, and I talked about the least privilege model earlier, so I can skip that. I had some extra slides about like secrets management and encryption at rest, but since we are out of time, I will skip them. And I would like to thank you for like staying all the way through this, I don't know, what's the word, very fast presentation. It's been a while since I hadn't presented that in such a short period of time, so I realized that I should have shaved even more things from the content because I still had to go faster than I thought, and I still had content that I had to glaze over. But what I would like to mention is that, first of all, the clusters that we have here are going to stay online like until later tonight. But since I don't expect anyone to be like spending their evening doing Docker stuff, if you want to repeat this or experiment with Docker, there is a completely awesome website called Play with Docker. Wait, I need to do some, yes. Yeah. So Play with Docker. First, you need to prove that you are a human. So if you are a robot but know how to click on a CAPTCHA, you can also access it. And once you are here, you have a Docker sandbox. You do add new instance. And boom, you get a Docker node. And you can do Docker swarm init. Well, there is a little tweak here. You have to indicate like an extra flag. But basically, you get a complete Docker environment, which is fully functional, except for one thing. It's going to self-destruct after 4 hours. So it's great to experiment and learn, not so much to host stuff. But if at any point you need to quickly check something with Docker, you can do that. And you can even have a cluster. Yeah, you can create multiple nodes and set up a swarm between them. And yeah, the last thing I want to say is that on container.training, when you have the self-paced version of the workshop, it's assuming that you're using Play with Docker, and so some of the instructions are updated to tell you how to use Play with Docker. That's it. Thank you very much.